Hello and welcome to the next lecture. In this lecture, we will continue looking at the data types in R programming. Matrices are a special type of vector in R. So they are not a different or a separate class of objects, but they are basically vectors that have a special attribute called dimension. And so the dimension attribute is an integer vector of length 2, where the first number is the number of rows of the matrix and the second number is the number of columns. And so if I create a matrix, an empty matrix with the matrix function, and I explicitly say how many rows and how many columns there are, this is not the only way to create a matrix, but it's one way. And so when I auto print the matrix by typing the object M and hitting enter, you will see that it will show me that first of all the matrix is full and is initialized with NA values. There's no values in here, and you can see that there's 2 rows and 3 columns, and they are labeled by the numbers in the brackets. If I call the dim function on M, it will give me the dimension attribute, which in this case it says there are 2 rows and 3 columns, because the first number is the number of rows and the second number is the number of columns. If I call the attributes function on M, you will see it returns a list where the first element is the dim element and it has the vector 2 and 3. So these are all aspects of a matrix, which is a vector that has a dimension attribute to it. Matrices are constructed column wise, so you can think of a matrix taking a vector and all the numbers are inserted in the matrix by column. So the first column gets filled, and then when you hit the maximum number of rows, then the second column gets filled, and then the third column, and so on. So if I create a matrix by taking the sequence 1 to 6, and then I specify that it has 2 rows and 3 columns, well, how does this matrix get constructed? So the way it gets constructed is column wise. So the first thing it happens is it takes 1, 2, and now there's only 2 rows, so it can only go to 2, and then that makes the first column. The second column is made up of 3 and 4, and then the third column is made up of 5 and 6. You can also create a matrix by creating the dimension attribute on a vector. So for example, I can create a vector that is a sequence 1 to 10 and then add the dimension attribute to it. So here I am using the dim function, but I am assigning a value to the dim attribute of M. So here I am assigning the vector 2 and 5. So what I am saying is I want to take this vector M and transform it into a matrix that is 2 rows and 5 columns. And so now after I have done that, I've got a matrix M which has 2 rows and 5 columns, and it's filled in the matrix column wise. Another way to create a matrix, and this is a common way, is by binding columns or binding rows. And so this column binding and row binding can be achieved by the functions cbind and rbind. So for example, suppose I have the 2 objects X which is sequenced from 1 to 3 and Y which is a sequence from 10 to 12. If I cbind these 2 objects, then I will get a matrix where the first column is 1, 2, 3 and the second column is 10, 11 and 12. So in cbind, both the vectors X and Y are combined column wise. So this is kind of what you might expect would happen. If I rbind those 2 objects, then the first row will be 1, 2, 3 and the second row will be 10 through 12. So cbinding and rbinding is another way to create a matrix. So vector is a special type of vector which is used to represent categorical data. So there are 2 types of vector. There is unordered and ordered. So you can think of this as storing data that have labels that are categorical but have no ordering. So for example, male and female, or you can have ordered vectors which might represent things that are ranked. So they have an order but they are not numerical. For example, you know, in many universities you will have assistant professors, associate professors and full professors. Those are categorical but they are ordered. So you can think of a vector as an integer vector where each integer has a label. So for example, you might think of it as a vector as 1, 2, 3, where 1 represents, you know, high, for example high value, and 2 represents a medium value and 3 represents a low value. So you might have a variable that's called high, medium and low, and underlying in R is represented by the numbers 1, 2 and 3. So vectors are important because they are treated specially by modeling functions like LM linear models and GLM generalized linear models, which we will talk about later, but these are functions for fitting linear models, and factors, generally speaking, are better than using simple integer vectors because the factors are what are called self-describing. So having a variable that has values male and female is more descriptive than having a variable that just has ones and twos. So for example, in many datasets you will find that there will be a variable that's coded as 1 and 2, and it's not easy to know whether that variable is really a numeric variable that only takes values 1 and 2. But the problem is that's not something that's coded in the dataset, so it's hard to tell. If you use a factor variable, then the coding for the labels, which is already built into the factor variable, and it's much easier to understand. So factors can be created with the factor function, and the input into the factor function is a character vector. So here I am just creating a simple factor with the two levels, and the levels are yes and no. And so x is a factor. You can see what it prints out is a little bit different from a character vector, in the sense that it prints up the values yes, yes, no, and then it has a separate attribute which is called the levels. And so the levels of this factor are no and yes. Okay, so there's only two levels. I can call table on this factor, and it will give me a frequency count of how many of each level there are. So for example, it will tell me there are 2 no and there are 3 yes. Now the unclass function strips out the class for a vector. So for example, if I call unclass on x, it will kind of bring it down to an integer vector, and you can see that underlying the vectors represent as 2, 2, 1, 2, 1. So yes, it's coded as 2, and no, it's coded as 1. Now it's not really essential for you to know this because you can just treat the factor as being a vector of yes and no, but it's used sometimes, and it's useful just to know underneath kind of how factors are represented by R. And so you see it's really an integer vector with the levels attribute of no and yes. The order of the levels in the factor can be set using the levels argument in factors. So sometimes this is important because in modeling functions, when you include a factor variable, sometimes it's important to know that what the baseline level is. And so the baseline level is just the first level in the factor, and the way this is determined by NR is critical. It's determined using alphabetical order. So for example, if I create a factor variable with the elements yes and no, then the baseline level will be the first level that's encountered, and because no comes before yes alphabetically, so no will be the baseline level and yes will be the second level. Now this may not be something that you might want, for example, a yes to be the baseline level and no to be the second level, and then in that case you have to explicitly tell R that yes is going to be the first level, and you can do that using the levels argument to the factor function. So now when I print out the x object, you see that the elements are still the same. Still they are yes, yes, no, but the levels attribute is reversed because we told yes to be the first level and no to be the second level. So there is a special type of object that we haven't talked too much about yet, and these are missing values. Missing values in R are denoted by either NA or NaN, which we talked about before. NaN is used for undefined mathematical operations, and Na is pretty much used for everything else. And so there's a function in R called is.na, which is used to test objects to see if they are Na, to see if there are missing values in that object. There's another function called is.nan, which is used to test for nans. So Na values can have a class too. So you can have missing integer values, or you can have missing character values, or missing numeric values, etc. And so even though it looks like it's all NAs, but the NAs can have different classes potentially, and then a nan value is considered to be also Na. So for example, a nan value is also considered to be missing, but the converse is not true. So an Na value is not necessarily a nan value. I've got a few different types of missing values listed here. So here I created a vector x which is 1, 2, Na, 10 and 3. So now this is a numeric vector, and the Na value in here is going to be a numeric missing value. So when I call is.na on x, what it returns is a logical vector, and the logical vector indicates whether each element of the vector x is missing or not. And so there is only one missing element in this vector, and so that is the third element. So you can see that the logical vector that is returned, the first two are false, the third is true, and the fourth and fifth are false. So the element that's true indicated where the missing value is. If I call is.nan on this vector, you will see that vector that's returned is all false because there are not any nan values in this vector, so everything's false. Of course, if I create a vector that has an AND, a nan value and an NA value in it, you will see that is.na returns true for both of them, but is.nan only returns true for the value that's actually nan. The last data type I am going to talk about here is the data frame. The data frame is a key data type used in R, and it's used to store tabular data. So of course tabular data make up a lot of what we use in statistics. Of course not all types of data are tabular, but because so much data comes and stores in a tabular form, data frames are very important in R. So data frames are basically represented as a special type of list where every element of that list has the same length. Right, so you can think of each column of the data frame as an element of the list, and of course in order to be a table, every column has to have the same length. However, each column does not have to be the same type. So the first column could be numbers, the second column could be factors, the third column could be integers, the fourth column could be logicals. It doesn't matter what the different types are. So unlike matrices where you have to store the same type of object in every single element of the matrix, data frame can store your objects of different classes, and so data frames also have some special attributes. The first special attribute is called a row name, and so every row of a data frame has a name, and this can be useful for kind of annotating the data. So for example, each row might represent a subject enrolled in a study, and then the row names would be the subject ID, for example. However, sometimes the row names are not interesting, and often you will just use row names of 1, 2, 3, etc. Data frames can be created by calling most often calls, the read.table and the read.csv function, and we will get into that a little bit when I talk about reading data into R. And you can also create a matrix from the data frame by calling the data.matrix function. Now you cannot, if you have a data frame that has many different types of objects, and then if you coerce that into a matrix, it's going to force each object to be coerced so that they are all the same. So you may get something that is not exactly expected. So data frames can be created besides using read.table or read.csv. You can use the data.frame function, and here I have created a very simple data frame where the first column is called the foo variable and the second column is the bar variable. The foo variable is an integer sequence from 1 to 4, and the bar variable is a logical vector with 2 trues and 2 falses. So when I auto print the data frame out, you will see it prints out the 2 columns, and here the row name, since I didn't specify any special row names, just defaults to 1, 2, 3, 4 because there are 4 rows. And then when I call the nRow function on X, I see that there's 4 rows in the data frame, and when I call the nCall function on X, shows me that there are 2 columns. One important thing here, R objects can also have names. So this is not true for just data frames. It's true for all R objects, and this can be very useful for writing readable code and self-describing objects. So for example, I am creating a vector that's an integer sequence 1, 2, 3, and by default there's no name. So when I call the names function on X, it gives me a null value. However, I can give a name to each element of the vector X. So for example, if I can say the first element is called foo, the second element is called bar, and the third element is called north. So now when I print out my X vector, I get a vector 1, 2, 3, but then each one has a name over it, which is the name I just specified. And so when I call the names function, I get the names that are associated with each element of the vector, that are foo, bar, and north. Lists can also have names, and so for example, here I am creating a list with the list function where the first element is called A, the second element is called B, and the third element is called C. And so when I print out the list, it prints out the names of each element and the values associated with those names. Finally, matrices can also have names. These are called dim names. So here I created a matrix from the sequence 1 to 4, and it's a 2 by 2 matrix. And so when I use the dim names function, I assign it a list where the first element of the list is the vector of row names and the second element of the list is a vector of column names. So here I want to name the rows A and B, and I want to name the columns C and D. So that's what I passed to the dim names function. And now when I print out my matrix, I can see that the row names and the column names are labeled as I wanted. So that's kind of a whirlwind tour of the different basic data types in R. So far we have talked about the atomic classes in numeric, logical, character, integer and complex vectors. We talked about how vectors can only have elements of the same class, and the main exception to that is lists, which can have elements of different classes. There are factors which are used for coding categorical data with ordered and unordered data. There are missing values that are represented by NAs and NANs. Data frames are used to store tabular data where each column can be of a different class. And finally, all our R objects can have names, which can be useful for creating self-describing data. See you in the next lecture where we will talk about reading data into R. Till then, ciao.